Welcome all to the next edition of Goat Seminar. Today we'll have José, Gaspar, Smutný talking about the parameterized complexity of maximum betweenness centrality.
Thanks for the introduction. Okay, so as Michal mentioned, the topic of this presentation is a paper that will be published in the Theory and Applications of Models of Computation annual conference. And yes, so this is a paper with Shimon Shirai. So an introduction of the title mainly, the parameterized complexity of maximum betweenness centrality. I'll begin with describing a bit what is centrality. Centrality measures are used in the study of social networks, and they give us information about the importance of nodes in a network. These are networks that model communication in some sense. So we have some nodes, they communicate, and we want to know which nodes are more central. There are many ways to look into this problem. So there are very straightforward and simple measures of centrality, like degree centrality, for example, where we only count the degrees of each node and we determine if it's central, if it has more neighbors. It's a very simple way of measuring centrality. It has some uses. However, we focus on betweenness centrality. Betweenness centrality, if you imagine a graph, we first assume that communication occurs along shortest paths. So if you imagine these are routers, then we assume that every endpoint in the network communicates using a shortest path of routers. So it won't go where uselessly long path. So that's an assumption we make. And we are interested in communication that occurs in these networks. We are interested in the vertices or the nodes that cover a largest amount of shortest paths that convey the communication in the network. I will get into a more formal definition later. Right now, it's just an intuition behind this. Of course, betweenness centrality is regards only a single vertex, but we can generalize this to groups of vertices. This is a very useful generalization, so we can study the way whole groups of vertices influence communication in the network, assuming that it's occurring along shortest paths. It can be used in the study of wireless networks, for example, with the router example. Also, covert networks. So I read some studies about the police investigations of criminal networks and trying to find relevant groups that influence communication among the network, which is, of course, interesting application. Also, biological networks. So for the study of the way some proteins interact with each other. And now, finally, our problem of interest, maximum betweenness centrality. Here, K maximum betweenness centrality. It consists in finding a group of vertices that has a maximal group betweenness centrality, or a group betweenness centrality that exceeds a certain threshold, if it's a decision problem. It's not an easy problem, as we'll see, in the sense of complexity, and it's our main concern in this paper. Now, there has been some work done already regarding betweenness centrality. It's not a new problem. However, from a perspective of traditional complexity, it is evident that the problem is very intractable. So there is no efficient way to solve this problem. And so we decided to attack this problem from the side of parameterized complexity. So study some parameters, natural parameters, structural parameters. I'll go into this a bit deeper. Okay, so that was the introduction. If you have any questions, you can ask gradually, otherwise just leave it at the end. Now, for the overview, I'll first introduce some notation, just so we know what we're talking about, for parameterized complexity and also for group betweenness, for betweenness centrality. Then I'll define the problem formally. Then we'll go, it's like the traditional hardness overview is really not the focus, neither of the paper or this presentation, so I'll just go through that quickly. And then I'll go through parameterization by natural parameters. That means the group size that we are interested in and the threshold. And that's also not the focus of this presentation. Also in the paper we deal with this. And the main focus of this presentation is a parameterization by structural parameters. So some parameters that tell us something about the structure of the input graph. We study vertex cover, distance to clique and budget, a combined parameter, and also distance to clique only, which is a more desirable result when we can focus only on the single parameter. And to conclude, I'll discuss some open avenues of research. Okay, so parameterized complexity. Just how many of you are familiar with parameterized complexity in some way? You just. Okay, so I'll go through it quickly, maybe for the online viewers. Parameterized complexity is a framework for the nuance analysis of complexity. So in traditional complexity, the information we get is the size of the input. That's what we work with, and we really don't know much about the input other than this. So the algorithms don't capture to great detail how the input influences the efficiency of the algorithms. With parameterized complexity, we additionally work with some parameters. That's why it's called parameterized complexity. It can be natural parameters, so parameters inherent to the problem, or some additional parameters that describe the input. And ideally, if the ideal result is when we can find fixed parameter tractable algorithms. What does this mean? This means that for fixed values of the parameter, we have a efficient algorithm, a polynomial algorithm. So we go from you can see, we go from a function of n in general to a function of k, a parameter, times a polynomial of n. So if you see if k is constant, then we have a polynomial of a function of n, which is a great result. It means that we can solve a problem more efficiently. And the concept behind this is that we move the complexity of the problem towards a parameter. So we say this problem is, or in an algorithm, if the value of this parameter is smaller or larger, then this affects the efficiency of this algorithm in such a way. So that it gives a profound, more profound understanding of the problem, of the complexity of algorithms for a problem. Now, of course, not every algorithm can be as efficient, or we don't find such efficient algorithms for every problem. Then we have an exponential class of algorithms, and these are algorithms we have of the form or the complexity and complexity from n to the OK. It's not as efficient, of course. So yeah. I won't go into much of depth. This is really not like the main interest here in the presentation. Finally, it is widely believed that not all parameterized algorithms are in FPT. This is a parallel to the N versus or P versus NP problem in traditional complexity. And to tackle this, the W hierarchy was introduced. So we basically say that there are some less tractable parameterized algorithms, and we assume that they are not equal to FTP. For our purposes, we have like a very basic use of the W hierarchy, and for us it suffices to show that a problem is W1 hard using parameterized reductions, and then we assume that this is strong evidence that there is no FPT algorithm for such problem for a given parameter. Now, the exponential time hypothesis is a assumption, a widely believed assumption about the complexity of satisfiability, a variant. And what it allows us to do is through, again, parameterized reductions, we can say this problem has a lower bound of such and such complexity. If this is not true, then we are able to solve satisfiability in like efficient way, and that would be very, we explain that this is not possible. So it gives us strong evidence that there is a lower bound of the complexity for algorithms for a set problem, again, with respect to certain parameters. Okay. And now the notation regarding betweenness centrality. We are working with simple connected graphs, so no multi-graphs, no directory graphs. And for any three vertices, sigma st denotes the number of shortest paths between S and T. So for these two vertices, it will be 1 because there's only one shortest path, that's 1 3. Sigma st of b denotes the number of shortest paths which contain a given vertex. So if I would mark st and some b, then sigma stb will equal 1 because there's one shortest path and it covers that shortest path. We can generalize this to groups of vertices. We have sigma st of a group of vertices. The principle is the same, so if at least one vertex is in this group, then it counts. And now the betweenness centrality. If we take every single pair of vertices and calculate the fraction of shortest paths that it covers, the vertex, and add all this for every single pair of distinct vertices, then we have its Betweenness centrality. You may notice that it's a number that corresponds to the probability of the vertex detecting communication if it occurs uniformly at random between pairs of vertices. And uniformly at random, using uniformly at randomly, the random picked shortest paths. And the generalization to group Betweenness centrality is quite straightforward. We only consider the shortest paths covered by a group, not by a single vertex. Okay, that's only the basic information. Also, the problem definition. We receive a simple connected graph, threshold T, and a group size K. And our task is to determine if there's a group C of size at most K, such that its group Betweenness centrality exceeds the threshold. So if we are interested if such a group exists. Now, for the traditional hardness of this problem, we know that this problem is NP complete. This was shown in the past. We show that K and BC is NP complete even for bipartite for planar graphs of maximum degree G. So even for a restriction of the input graphs, we know that this problem is NP complete. And in contrast, if we restrict even more the input graph, so if it's either a path or a cycle, then the problem becomes solvable in linear time. So we really have to restrict the input graph a lot in order to obtain some tractable results without the framework of parameterized complexity. Again, I'll go through this only quickly. So the question arises: okay, within the framework of traditional complexity, we are basically finished. There's like really nothing else we can do. What we can do is study additional parameters. So we begin, of course, with natural parameters. Those are the parameters inherent to the problem. So it's the group size K and the threshold. And as I mentioned, I won't go in too much detail about this. I've already talked about this before, and I don't think it's the. I'll just go through it quickly. Well, we discovered that with regards to the group size, that the problem is W1 hard. This means that we do not expect that an FPT algorithm for K and BC exists, parameterized by the group size only. We also discovered that the basic brute force algorithm, so just taking every single group of size K and testing whether its group Betweenness centrality exceeds a threshold, that this brute force algorithm is already optimal under the exponential time hypothesis. So there really is no space for improvement here, asymptotically. These observations also hold for n-q MBC problem. So it's very similar. Instead of saying that the parameter is a group size, it's the number of vertices not in the well, a group of size n-q. And the same observations apply. So the brute force algorithm is already optimal under ETH, the exponential time hypothesis, and the problem is W1 hard. Okay, so that's the group size, and then we have the other parameter, the threshold. Now, for the threshold, is parameterization by the threshold is not as straightforward because we usually assume that we have, if you recall, a function of the parameter times and to some constant. However, if the parameter is some function of n, so for example, it can be large and for example n squared, then this is not like a really great solution because here we could have some 2 to the something, a very inefficient function of the parameter, and the threshold can be quite large in this case. So we are still figuring out how we can work with the threshold. Maybe mark it as a percentage of the maximal possible value for the threshold, or somehow work with this. However, this is how far we got with natural parameters. And the following step was looking into structural parameters. And the structural parameters we studied were the vertex cover number, the distance to clique, and group size combined. These two algorithms, the algorithms for these parameters are very similar. I will discuss the main principle behind them. And then only the distance to clique, which was done using a nice trick, and also the twin cover number. I won't talk about the twin cover number here because it's a slightly different method. We don't have so much time. However, I'll touch on the other three parameters. Before we begin, I would like to show a lemma that is the basis for the algorithms that we use. This lemma is called the twin sect change lemma, and I'll begin by saying like the main idea behind it. So imagine we have some group of vertices, and all these vertices have the same neighborhood. So they all share the same neighborhood. Yeah, you can imagine it. And what we are trying to say is that these vertices, from the perspective of group betweenness centrality, we can pick, as long as it's a fixed amount, we can pick any number of any selection of vertices, and we really don't care what the selection is. We only care about the amount. And what this allows us to do is say, okay, if I'm going to pick at most k vertices, then I can pick these k vertices, and I don't care about the rest. I cannot remove them from the graph, but it allows us to reduce the search space for groups with maximal group betweenness centrality. And this is the basis of the algorithms we use later. So formally, we have two sets, x and y, and x, they have the both sides, of course. And for every vertex that's in them, we know that they share the same neighborhood, except for the connection between them. So we know that x and y are right there, completely disconnected or fully connected. That's the only two options. And that they share the same neighborhood otherwise. And then there's a group C, and again, a subset of vertices in sharing no vertices with x and y. And we, the lemma tells us that it holds that the group betweenness centrality of C union x equals that of C union y. This is the result we are after. So basically, we can substitute vertices, which are twins. That's the idea. We can exchange twins. Okay, so the proof, it's very abridged. However, I think it's not that hard to follow. By definition, if you recall the definition of group betweenness centrality, the group betweenness centrality of C union X is the fraction of shortest paths it covers. Okay, so say some. And now we wish to show, because here the shortest paths between U and V don't change for any pair. That's a property of the graph, and we are not modifying this. So if we wish to show that the group betweenness centrality remains unchanged, then it suffices to show that the number of shortest paths covered by C and C union X equals to that of C union Y. We do this by showing an inequality in both directions. So by showing that there are at least as many shortest paths covered by C union X as there are shortest paths covered by C union Y, and then backwards. Now, how do we show this? For any UV vertices, consider a path Q, a shortest path UV, with at least one vertex from C union X. Okay, so we know that the shortest path is covered by C union X, and we wish to show that C union Y is at least as large as the number of shortest paths covered by C union X. So, and we have two possibilities. Either this shortest path contains a vertex from C union Y, then trivially it's also accounted in the number of shortest paths covered by C union Y. That's pretty clear. Otherwise, there's no vertex from C union Y in this shortest path Q. And what we can do is we can make, if we enumerate the vertices from X and Y, so it's going to be x1, x2, and so on. And then we have y1, y2, and so on. Recall that the sets have the same size. Then what we can do is simply swap the vertex from X that the path contains. And we are sure that the vertex contains a vertex from X because it's covered by C union X. That's in our assumptions. And by doing this, we ensure that for every single shortest path that is covered by C union Y, C union X, there is a shortest path that is covered by C union Y. So the inequality holds. Again, by the same logic, we can do the inequality in the opposite direction, and we arrive at the conclusion that the number of shortest paths covered by C union X is equal to that of C union Y, and thus the group betweenness centrality is equal for both of these sets. And this is a very useful result for us, because as I mentioned, it tells us that for a group of vertices that has the same neighborhood, we can, as long as the amount is fixed, we can pick any particular selection, and it doesn't matter. Because they have the same neighborhood, they are indistinguishable from each other, in a sense. So that was a change lemma. Now I show how it's applied for the description of our parameterized algorithm for K and BC parameterized by the vertex cover number. Because the vertex cover number, I'm not sure it's an introduction, but it's a number. The vertex cover number is the size of the smallest vertex cover in a graph. It's very, very well studied for many problems. Yes, so we also decided to study it with regards to group betweenness centrality. Also, there's maybe a small comment here. There's a lot of like intuition behind this, because if every vertex cover completely detects all communication in the network, if you think about this, because every single pair of vertices is either in the vertex cover, so the communication is detected, or is not in the vertex cover, but needs to pass through the vertex cover in order to detect communication. So one thing is that this parameter is going to have some influence in the problem. Okay, so how does it work? We basically just apply the twin-stick change lemma. We begin by picking a minimal vertex cover, M, and we group every single vertex that's not in M into groups depending on their neighborhood in M. Of course, the amount of these groups is at most 2 to the size of the vertex cover, depending on which vertices they are connected to. And now what we have achieved is that we have our vertex cover M, and then we have groups of vertices which have the same neighborhood.
Please use a different pen.
Like the color?
Yeah,
Yes.
like the color.
Oh, sorry.
Like a red one, preferably.
I don't think I can. Oh, okay, it works. Thanks. So we have the vertex cover, and we have groups of vertices. They are disconnected because it's a vertex cover, and these vertices all have the same neighborhood. Every single vertex in here. So this one may be here. This one may be here. And what we have basically done is divided the vertices not in M into groups of twins. It's very like the key moment for this, because what we can then do is we say, okay, from this group of vertices, I will never pick more than k vertices because that's my group size. It wouldn't make sense to consider more than k vertices, so I can pick only k vertices from here, and only k vertices from here, only k vertices from here. And what we have done is that we have greatly reduced the number of vertices we need to consider. We can simply color them or just to distinguish them. But suddenly we are working not with a function of n vertices, but with only k to the l vertices. K times 2 to the l vertices. And if we simply check every combination of these vertices that we have selected, then we arrive at an FPT algorithm, because we got rid of the dependency on n for the number of vertices that we need to consider, which is a fine result. Now, for our final set, you remember when I mentioned that a vertex cover detects all communication? If the group size parameter is larger than the vertex cover number, then we can simply pick the whole vertex cover number, and we trivially have a yes instance. And so what we can do is we can assume that k is always smaller than l, and in that case we can replace k by l in our algorithm. So we don't need to be dependent on the group size parameter, and we have an FPT algorithm for k and bc parameterized solely by the vertex cover number, which is of course ideal. Now I'll go with the approach. It's basically the same approach, and it can be used with the distance to clique parameter. I'll show the parallel, and then I'll show the alternative way. So the distance to clique, we have a graph. We have a modulator to clique M, and that's a group of vertices that when it is removed from the graph, we are left with a complete graph. So a clique. Maybe just for intuitive brain. We have a clique, and then we have some 2 vertices. So if we remove these 2 vertices, we are left with a clique. So this is a clique modulator to clique of this graph of size 2, which is, and the distance to clique of a graph is the size of its smallest modulator to clique. And now, when you think about this, the vertices not in the clique modulator are also twins, depending on their neighborhoods in them. So the approach is practically the same. What we can do is we take all the vertices not in the clique modulator and group them according to the neighborhoods in the modulator to clique. We obtain again some groups of twins. This time they are fully connected. This is not a problem by our definition of the twins exchange lemma. And we can again apply the twins exchange lemma, pick only k vertices from each of these, at most 2 to the distance to clique groups. And we again greatly reduce the number of vertices we need to consider and are left with an FBT algorithm. The only difference is that, as before, if we pick the vertex cover, then we detect the communication. This is of course not the case with the distance to clique parameter. We cannot simply pick the modulator to clique and say, okay, we're detecting all communication, because this is not true. On the contrary, we can find instances where no vertices are picked from the clique modulator for a group with maximal group betweenness centrality. So this FPT algorithm is parameterized not only by the distance to clique parameter, but also by the budget. It's a combined parameter in this case. We wanted to overcome this, and Shimon came with the idea of using interior linear programming. And that's the approach we use here. So what do? We take again the graph, its modulator to clique of size L, and we again group the vertices into at most 2 2DL groups, or types, I think they're called here. Yeah, types, depending on their neighborhoods in the modulator to clique. Now, what we do is we guess a subset of M that will be in the solution, M star. And I say guess because we are going to try a lot of guesses until we arrive either at a yes instance or until we deplete all guesses and then say it's a no instance. But we just say, okay, I pick these vertices from M. These are going to be in the solution. And then we only need to consider vertices not in M as to whether they will be on the solution or not. Now, for every pair of vertices which are not in the selection but are in the modulator to clique, then we compute all shortest UV paths between them. And this can be done because it's not a large number. It's limited by this. This is a lemma. I am going to this, but you can trust me that this is true. Basically, the idea is that every shortest path contains a small amount of vertices in graphs with the clique. Small amount of vertices from the vertices not in the modulator, because it's a clique, so we can always shorten the path. Now, every single shortest path can be partitioned into 2 to the number of types, kinds, based on the types of vertices that they contain. So if we have, I use back again. If we have, here we have one type, and these ones are of the second type. So a shortest path may contain a vertex from this type and this type, or only this type, or only this type, and these are the combinations we are checking. And finally, we can construct an interior linear programming problem where the variables correspond to the types of vertices. So again, recall that these types are twins. So we really don't care which particular vertices we pick. We only care about their amount. And that's what the interior linear program will tell us at the output. So this variable needs to be 3, this variable needs to be 4. So we know that we are picking 3 or 4 vertices from a set group. The constraints ensure that we actually pick the correct amount of vertices, and also that we don't pick more than the actual amount of vertices in the groups. So we need to check this. And the actual hard work is in the optimization function. So that's where we say, okay, if you pick this vertex and you cover this path, and the group centrality is this amount, and we can solve this using an FPT algorithm for linear programming, parameterized by the number of variables, which, if you recall, is not a function of n. It's just a function of the parameter of the distance to clique. And if the resulting group betweenness centrality is less than the threshold, then we don't say no instance. We simply try a different guess. And if it exceeds the threshold, then of course we conclude that it's a yes instance. And otherwise, if we exhaust all possible guesses, then we conclude we have no instance because we didn't find any solution. Now, the main outcome is that we have an FPT algorithm that is dependent only on the distance to clique. So we got rid of the group size dependency, which is of course nice. How much time do we have? Okay, maybe I'll touch quickly on the twin cover number. So what the twin cover number tells us is that if we have a twin cover, and when we remove it from the graph, we are left with these joint cliques, such that every vertex has the same neighborhood before we remove the modulator. So we could have a triangle, and every single clique every vertex from each clique has the same neighborhood on the modulator. So it could be something like this. Oh, it's not very visible. Now,
could you please take a different pen?
So green is not working, black is not working. I'm sorry. A different one. Okay, I think you just have to imagine it. I sadly didn't prepare an image. Well, however, the idea we can apply is that, again, we observe that the vertices are not twins, but they are very close to it. The only problem is the connections between vertices, like different cliques that have the same neighborhood. So what can happen is that we can have a clique of size 5, for example, a clique of size 4, and they both share the same neighborhood in the modulator. But they are not connected between each other. So they are not twins. But if we play around a little bit, we can, if we pick the vertices carefully, we can also pick only k vertices from the groups. So basically, it's just one application of the twin sect change lemma. It's just a little bit more sophisticated, and yeah, I will go into that much detail. And okay, so now to conclude, what further work do we see or open avenues for research? We would like to find additional lower bounds for the complexity of the algorithms we found, in particular structural parameters. So right now, we don't know, for example, if the vertex cover algorithm for FPT for MBC parameterized by the vertex cover is optimal. If it's already reached the lower bound, or we can improve it further. So this is something that interests us, as well with the distance to clique and the twin cover number. We would also like to study the parameterized complexity with regards to the twin cover number alone, because this approach, it also leads to a dependency on the group size as a parameter. So we would also like to remove this dependency. And yes, for the third point, there exists an algorithm for KMBC on trees, which is polynomial. It runs in polynomial time. It has to do with the fact that in trees, every single pair of vertices has a single shortest path. So it's a fairly strong restriction of the input graph. However, we would like to see if KMBC is in FPT when parameterized by the tree width, which is also very well studied parameter. And finally, we'd like to study kernelization in the context of KMBC. Right now, as I mentioned, we usually only disregard vertices. We do not actually remove them from the graph because this can affect different vertices differently. If you imagine that we remove a vertex, then the vertices that are closer or more connected to it will their centrality will decrease by a greater amount. So we cannot just remove them. We can disregard them. But we like to study if there are ways we can reduce the size of the input by doing some careful tweaking or some sort of calculation. So this is all. Thank you. Also, thank you for the student summer research program supported this, and mainly to Shimon for writing this together. And this is all. Any questions from you?
First, let's thank the speaker.
Oh.
Maybe I
Yeah.
So at some point you mentioning hardness, etc., and I was expecting to see something. Do you have any hardness results from parameterized point of view, maybe for some really small? I miss it.
It was for the I'm going a lot back.
Okay.
For the natural parameters,
okay.
we showed that it's W1 hard for the group size. It's a nice proof. It just it's a little bit lengthy, so I didn't want to present it fully.
Mm.
Maybe if you don't mind, I can just maybe present it quickly. Yeah. So basically, the idea is we reduce from the partial vertex cover problem. We are basically saying that, and what we do is we have the input graph, and we add some gadgets to increase the centrality corresponding to covered edges, previously uncovered. So we have a lot of vertices here, and they are all connected with this. I'm sorry, it's not visible. I know.
Yeah. You cannot see it anyway.
Yeah, that's better. Okay. That's a bit better. Okay. So we have some gadgets. These are completely connected cliques. And we also add some guard vertices between no edges. And they are connected between, they basically replace this edge.
Mm-hmm.
And we show, basically what happens is that there is a correspondence between the amount of covered edges and the group betweenness centrality. So if we get a yes instance here, then we know that at least some amount of edges was covered. So this is how we show that the problem is W1 hard. There's more detail and more math,
yeah,
but that's the main idea. Okay.
Nothing from structural parameters, I don't know. Cluster deletion.
Parameterized by degree.
Okay.
It's also parameterized by unit.
Or is it unfair?
We don't know more.
Okay.
Yeah, but that's also something we interested in.
Right. So, any other question?
Thank you. Yeah.
Would it make sense to normalize the bound we are heading for? It probably is something like between n and n squared or something like that. Would it make sense to divide it by n to make it in some reasonable range?
I don't remember if we tried this actually. We considered maybe decreasing because what's the maximum value? It's the number of pairs in the graph times 2, because that's the maximum number of shortest paths that can be covered. Not shortest paths of pairs. So we considered maybe like decreasing it by some value. So it would be like
Dividing it by
no decrease, like just shifting it down.
okay.
And just testing if it's a little bit above a certain value, then if that's the parameter that would be useful for us. Maybe the division. Yeah, it's something we want to tackle definitely, to just be able to say, okay, we have a parameter algorithm for the threshold, or maybe the problem is W1 hard for the threshold or so.
Okay. So if there are no more questions, then let's thank the speaker again.
Thank you.